one reaction that organometallic compounds will do, and it usually is a reaction we don't want them to do, is that alkyl lithium and alkyl magnesium halide compounds are strongly basic, which means that they will react with water or alcohols anywhere that we have them in our molecules, or if we have them in our reaction mixture. So we need to actually be very careful about how we perform organometallic reactions to keep water away and to make sure that we don't have any alcohols in our molecules, because if there are any alcohols in the molecule, we will not get the organometallic to add our alkyl group the way that we would hope it would. For example, if we have butyllithium plus water, it would form butane plus lithium hydroxide. I hope that you're comfortable determining which direction this reaction will proceed, since we've been talking about pKa's and reaction directions since the beginning of Organic 1. So you have to look at the pKa of the acid on each side of the reaction. So on one side it's water, and the other side is butane. So pK of water, 15.74. The pK of butane is about 60. So which way is this going to go? It's going to go completely to the right. The equilibrium lies more than 10 to the 34 times to the right for every one time it reverses towards the alkyl lithium compound. So what that means is that if there is any water around anywhere near an alkyl lithium compound, our alkyl lithium compound will be destroyed, and what we'll end up with is alkane and some base like lithium hydroxide. The same can be true if we react with some kind of an alcohol around. So here I have an alkyl magnesium bromide, or a Grignard reagent, and I'm reacting it with propanol somehow in the solution. And again, what happens, my carbon minus is going to come over and deprotonate my alcohol to give an alkane plus my alkoxide. And once again, we can look at pKa's. So the pKa here is 43. The pKa here of alcohol, about 15.2. And we can determine which way this reaction will go. It's going to go completely this direction, towards the weaker acid. So the stronger acid is the one that's more likely to give up its proton. How much more likely is the alcohol to give up its proton than the benzene? Almost 10 to the 28 times more likely. So that reaction lies near all the way to the right. So that's the first thing to realize, is that anytime we're going to do a reaction with organometallic compounds, we have to very carefully control to keep water and alcohols out of the reaction mixture. What reactions do we want our organometallics to do then? One of the very useful reactions that you can do with an organometallic compound is you can react it with a carbonyl. So I've got a negative on carbon here, I've got a positive on lithium. And so the same rules that we always use still apply. You want to decide who has electrons and who wants them. Our organometallic carbon has electrons, so then we have to look at our carbonyl and decide who wants them. Remember, there's a delta plus on the carbonyl carbon, delta minus on the carbonyl oxygen. The organometallic has electrons, the carbonyl carbon wants them. As the electrons add here, we have to break one of the pi bonds and push those out onto oxygen. Now we've formed a new carbon-carbon bond, which is a very valuable thing to do. And we get to the same place where we were before with addition versus substitution reactions. If we don't have a good leaving group, it has to do an addition. If we do have a good leaving group, it can do a nucleophilic acyl substitution. So if this electron pair comes back down, I've got methyl, methyl, methyl are my three groups, so there is no good leaving group. So the only option is to react with something like water and reprotonate. And we can do this to reprotonate the alkoxide to form an alcohol. In this example, we made a tertiary alcohol because we started with a ketone. If we start with an aldehyde, and I'll change the reaction just a little bit just to show the variety of things that we can do. Let's use methyl magnesium chloride this time, so it's a Grignard reaction. The methyl group again will add to the carbonyl. Again, we don't have a good leaving group. We only have carbon, carbon, and hydrogen, all poor leaving groups. Reprotonate again with water. And now you've made a secondary alcohol. The great thing about this is that you can really control to get any alcohol that you want. For example, this time I made 2-propanol. But what if you wanted 2-pentanol. See if you can draw the starting material that would be required to end with 2-pentanol. And there are actually two different ways that we could do it. One, we could start with butanal, treat that with methyl magnesium chloride, followed by water, and that would form 2-pentanol. Or we could start with acetaldehyde and add propyl magnesium chloride, followed by water, and that would make 2-pentanol. So there are a couple of different ways that we could do that. Now you could also make a primary alcohol if we start with formaldehyde. However, this isn't probably the most useful reaction because you can probably buy most primary alcohols that you want. However, if you want to make a primary alcohol, you could do something like add propyl lithium or the Grignard, either one, followed by water. And the propyl group will add to give us our alkoxide, which once we add our water, gives us our primary alcohol.